All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for this class. Just ask you to just guide our steps today. Help us to understand a little bit more about advanced calculus and just help us to understand the calculations today, Lord. In your name I pray, Lord Jesus. Amen. So the book I picked to teach advanced calculus back in 2009 was this Advanced Calculus with Several Variables by C.H. Edwards, Jr. Mostly because it's a Dover book. It's cheap, but it is, it's a good book. It has its has its shortcomings here and there, and people who are more of a stickler for clean proofs, kind of like, it's not a very good proof and stuff like that. But I think overall, it is, a worthy book, and so anyway, there's more to say from here eventually, but today I was going to focus on the inverse and implicit function theorems and sort of their intuitive proofs, and perhaps we will endeavor to give some indication of the non-intuitive proofs in here as well, since I'm trying to teach this course at a slightly higher level than I usually teach the regular advanced calculus course, right? Now I have proved these theorems, like honest to goodness proved them at various points in my advanced calculus teaching, but it's been a little bit since I've done that, and I really should study ahead before I try to attempt that, because there are some pickier points on the full proofs that I am not fresh on, and I'd probably just muddle. But let us get to it. Let's talk about the inverse and implicit function theorems. Now, I warned you there would come a time when I stop proving things for, norm linear spaces, and that time is now. So, although I think I have given a test question before in here where I asked people to derive the inverse or either inverse or implicit function theorem for a norm linear space, because I think there's a way to do it. If you prove the theorem in Rn, you can kind of like lift it up to norm linear spaces just through like coordinate maps. But so maybe we'll do that. But here, let's suppose we've got a function, really a map, which is from some the domain of f is some subset of Rn, and it's mapping to Rn. All right. Then the question is, can we find an inverse function in this context? Or at least, can we find a local inverse, right? So just a reminder about how this works, the n equals 1 case, right? I think it's worth our time just to take a second to drop back down to n equals 1, right? And there you're talking about a function, right, from some subset of the reals to the reals, right? And so in that context, we have, graphical tools. We can look at like, whatever, the graph, right, y equals f of x, and we can ask, is that function invertible, right? Well, obviously not in the global sense, right? But then we can ask a more delicate question. We can say, okay, well, does there exist, let's say, some interval? Maybe just keep it open for the sake of, some open interval of the domain for which f restricted to that interval, is 1 to 1. And if it's 1 to 1, then we can define an inverse mapping for that, right? And then of course we can dump the codomain for the range and have an honest to goodness bijection, right? If we want. So where does calculus enter into this story? So if I pick, if I pick this point, right? Then okay, fair enough. Like you can see, I could use this, right? I could use that for my interval. And if you look at, this portion of the graph, well, it definitely passes the horizontal line test, right? So where do you get into trouble? Yeah, where the derivative is 0, that's where there's trouble, isn't there? Like here, we'd have f prime of, let's say, a equals to 0. And if you tried to find a local inverse there, you'd be in trouble because you necessarily you're not going to get injectivity if you're on both sides of that critical point. Now, it doesn't have to happen. It's possible that the derivative is 0 at a point, and yet you still have local injectivity. Like, standard example of that is the cubic. Right? If we look at y equals x cubed, it has derivative 0 there, right? But it's still, in fact, if this is f of x, in fact, not only does it have a local inverse, it in fact has a global inverse, right? F inverse of y is the cube root of y, right? You can solve for x. You get x is equal to the cube root of y. That's the global formula for the inverse there, right? Fine. So it seems like the derivative being non-zero, well, first of all, we have to be careful. If the derivative is 0, we can't say for sure that the local inverse, even the global inverse, doesn't exist, right? So at best, we're talking about a condition to guarantee, a sufficient condition to guarantee the existence of a local inverse. To prove that there didn't exist a local inverse, that would require further analysis, which is probably not really so much advanced calculus as it is, like some kind of like higher level pre-calculus of some sort or another, algebra really. All right. Now, so that's just the backdrop, right? So let's stop with the one-dimensional and let's go to n-dimensional. So we're looking at a function, right, which is f of x is equal to, let's say, f of x naught plus f prime of x naught times x minus x naught. So here, this is Edwards' notation for the Jacobian of f at x naught, right? It's literally like partial f partial x1 partial f partial xn at x equals to x naught, all right? So this is, and we can be, and we have a more, so this is typically, well, I don't know, now I'm, see, what I don't usually include the error term here. All right. I mean, we could. Tell you what, I'll include it here just for giggles. So we got plus what? The error term in f. We'll say it's a function of x in this context, right? So in this context, we would be given what? That the limit as x goes to x naught in our current formalism of the error term of x divided by the norm of x minus x naught, that guy has to equal 0. That is essentially a sneaky way of expressing the vanishing of the Fauché quotient, right? That's all that is in some sense. And yet it does seem like more sometimes to me. I mean, I think distinguishing those two things, it's somewhat in the same realm as like distinguishing 3/2 from, 15/10 or something stupid. Okay, anyway, now what? So, you notice down here, to find the inverse function, I wrote down f of x equals to y, and then I solve for x. Okay? So, let's do the same, but now we've got a vector y. Y is equal to f of x naught plus f prime of x naught times x minus x naught plus my error term, which I'm going to suffer for a while. So to find the inverse function, what do I need to do?
Solve for x naught.
Solve for x. Yeah, solve for x. And if we solve for x, what do we get? Well, we got to do a little math here, right? So we got y minus f of x naught minus the error term equals to what? F prime of x naught times x minus x naught, right? Now keep in mind, don't be deceived. What we're writing over here, this is a matrix column product. Matrix column product. And so, well, the condition that over here, we needed f prime of a not equals to 0. Like if this is x naught, let's say, we needed f prime of x naught not equals to 0 is, a sufficient condition to have, well, we need f prime of x naught not equal to 0 near the point, don't we? But here's the thing, is if we have a continuously differentiable function, right? A continuously differentiable function, one which has a derivative, but the derivative is also continuous. If the derivative is non-zero at a point, it has to be non-zero everywhere near the point as well. See, because a continuous function can't jump from being non-zero to being 0 in like an infinitesimal interval. Like it takes some space for it to happen. And so by similar reasoning here, if I assume that this is an invertible matrix, and I assume that we have continuous differentiability of the map, it stands to reason that the Jacobian matrix of the map is invertible near the point. So actually, but anyway, we're just going to use that. So we multiply by the inverse to this, right? So we have, I guess I'll flip back to the Jacobian notation. So we have the inverse of the Jacobian matrix times x naught times this y minus f of x naught minus the error term of f. All right. And oh, see right here, this is why I'm going to have to give up on my error term. I have to give up on it. See, because I can't undo this x dependence. Like I can't do it. I can't hack it. So I had to give up on that. So you know what I can say though is I can say, okay, well, fine, all right. You know what I can do? I can say this. Well, it's approximately x minus x naught, right? That's true. So to an approximate truth, x is equal to x naught plus, the inverse of the Jacobian here at x naught times y minus f of x naught. And we could define this to be like g sub naught of y. Well, g sub 1. Because we would probably want to say, we'd say here g sub 0 of y naught is equal to x naught, where we would naturally define y naught to be equal to f of x naught. So like the most lazy approximation of a multivariate function is just to replace it with a constant function, right? So the constant function is simply replacing f of x with y equals f of x naught, right? So how do you invert that? Well, you send y naught to x naught. That's the stupidest inverse possible. The constant inverse, right? That's definitely not an inverse. Anyway, but it's an approximation for the...
Yeah.
All right. This is the next best approximation, like this.
So it's not an exact inverse.
No. No, this wouldn't be. But what you could do is you could define gn plus 1 of y to be equal to gn of y. All right. Minus, well, the Jacobian of f at x naught, the inverse of that, times what? Times f of gn of y minus y. Let me think about this. What would be f of, what was f of g0 here? Sorry, I'm trying to see the pattern. This is my theorem 4.1.2. Wonder if I have a typo here.
So we got multiple approximations that get better every time
That's right.
to the inverse.
Yeah, let me check on this. This is theorem 3.3 on page 185 of Edwards. I feel like I might have an extra symbol there. No, I don't. All right. All right. Let's see here. Maybe I should just write it down. Maybe I'm just being dumb. So n plus 1, right? So I'm trying to see how this formula reproduces that.
How did you derive the G plus 1?
I did not derive it. I derived this by simply solving the linearization equation for x. All right. So did I do that correctly to start with? Because if I did that wrong, then it's not surprising. So I subtract it to the other side, and then I multiply by the inverse of this. I get that, and I just add x naught to the other side. All right. So like, what would g sub? I guess the question is, what is g sub 0? G sub 0 of y. I said g sub 0 of y is just equal to x naught was my claim. I thought that's how we start it. I mean, if that's the case, that this tracks, right? G sub 1 is g sub 0 of y, which is x naught. Okay? And then the question is, how did that over there get flipped like that? Now, I think part of the problem is that there's a, oh, you know what it is? I'm a dummy. Check that out. There's a minus here, right? Okay, there's a minus there. That's what I'm missing. Duh. Wow, what a dummy. So this is f of g of, there it is. That is f of g naught of y is equal to f of x naught. All right, so we got the pattern. I mean, we have coherence of this with that. Okay, so let me explain, at least sketch the logic here, okay? So the logic is, if you can, so you solve, right, the, basically solve the tangent, the linearization of the nonlinear y equals f of x formula. Like you add x naught, we solve the linearization for x. That gives us our first approximation. The zeroth approximation is done. And then the sneaky idea is to realize that we can just keep doing this. We can just keep basically taking, you know, this, like g2, we write out g2. g2 of y would specifically be equal to, you know, g1 of y plus, you know, it's always the same matrix. See that? That's nice. And then you multiply by what? Well, and then you put a minus here to keep with the formula. Minus, and then you do f of what? Of g1 of y, which was, well, x naught, plus the Jacobian of f inverse of x naught, times y minus f of x naught, that, minus y. So actually carrying out this iteration, it is a fantastically technical iteration to actually carry out for a given example. It is an onerous calculation, like it is nasty. So this is primarily, I would say it's, for me, it's primarily of theoretical use. But you know, but it's a very simple thing that we're doing. We're just feeding, the idea is simple enough. If this approximates, you know, the inverse, then if I plug in the approximate into the approximate again, maybe that's a better approximate. And there's more that could be said here. It's basically it's a simple. If we first discuss Newton's law, Newton's method. Newton's method, we usually call it Newton's method. This is really closely based on Newton's method. But yeah, the theorem is that given the invertibility and the continuous differentiability of f, then this recursively defined sequence of functions I'm defining right here, well, guess what? That sequence of functions converges, all right? And I think I'm now remembering where I have to talk about the function norm. That converges. That begs the question, what do you mean a sequence of functions converges? Right? That's one thing. So whatever we mean, that sequence of functions converges. And in fact, the limit function exists. And it serves as the local inverse for the function. And not just that, you actually get the differentiability of the inverse from this. All right, so long story short, the theorem is pretty easy to understand. The theorem simply says this: if your function f has a invertible Jacobian at a point, and your function is continuously differentiable at that point, then there exists a local inverse to the function at said point. And there's more, and that local inverse can be obtained as the limit of this recursively defined sequence of mappings, which is based on an analogy to Newton's method. Now the proof that this converges is actually deeply beautiful and interesting, and it's using something called the contraction mapping principle, which we should talk about.
And why is the Jacobian vertical?
Oh, yeah, so that's a good example. So we'll come back to the proof, but let's just focus on the statement of the theorems today for the time being. So here, how about this one? F of x, we'll do f of x, y, z equal to, like, let's go with like x, y, z, z, all right? So there's a mapping from R3 to R3. I'm quite certain that it's not globally invertible, all right? And I'd actually like to spend some of our, so like we could talk more about the proof some other day, because there's some significant heavy lifting of analysis that we're going to have to do that. And I'm not sure I'm up to it today. So here, the Jacobian, what does it look like? Well, exactly, yz, 0, 0, and then what we got? xc, z, 0, and then, okay. All right. So when is this Jacobian invertible? Simple enough, we calculate the determinant. And in this one, yz squared is the determinant. So if this is not equal to 0, then that implies that there exists local inverse by inverse function theorem. Well, let's call it the inverse mapping theorem in our case, right? Because the inverse function, well, I don't know. People call it the inverse function theorem. You call it the inverse mapping theorem. Some people want to make a distinction between mapping and function. They reserve function for a function. A function is something that has a real or a complex value, whereas a mapping, I do not make these nuanced separations in map versus function. Like, map and function are synonymous for me. All right, great. What's its formula? How do you find that? So here's what you do is maybe you let u vw equal to x, y, z, z, right? And you solve for x, y, and z. What we're going to find is that the obstacle for having the formula is going to be exactly where the derivative gets messed up. You watch. It'll happen. Like, we have trouble when y equals to 0 or when z equals to 0 here, right? So let's see what happens when we solve. Now z is easy, right? Z equals to w apparently, right? And then we've got, well, yz is equal to v. So therefore, y is equal to, what is it? V over z, which is v over w, right? Check that out. We needed z not equal to 0 there, didn't we? Not an accident. See, because while I gave you the warning of the cubic one with the saddle point actually having an inverse. More often than not, the theorem goes both ways. Like, it's locally invertible if and only if the derivative, if and only if the inverse matrix is invertible. That's not a theorem. There are counterexamples like that, but as a rule of thumb, it's not surprising when it happens at all. X, Y, Z equals to u. Therefore, x is u over yz, right? So now we need both y and z non-zero, right? Well, surprise, surprise. And so that's u over v over w. And then what was z? Oh, w, right? So that's apparently u over v. Put it all together. What do we got? We've got f inverse of uvw equals, well, apparently u over v, v over w, and w. And of course, this is an abuse, right? I should say f restricted to some appropriate set. It's the inverse of that, right? It's not technically the inverse of the whole function. The whole function's not invertible, I don't think. Actually, I don't know. Is the whole function invertible? Well, like I just said, we have trouble with y and z being 0, right? Like, let's see here. We could put like f of 1, 0, 0 is equal to f of 1, 1, 0, right? See that? If you plug in z equals to 0, it automatically makes all three of those 0. So I can make y whatever I want, and it's still going to be 0. Like if I put 0 into the in other words, the inverse image of the 0 vector, this is 0, right, is equal to what? We have to have z for 0. Z has to be 0, but x and y are anything. So this is exactly x, y, 0, such that x and y are just real numbers. Or if you like, R2 cross 0. And I think if we have well, I'm just trying to, I mean, obviously, what I'm trying to figure out at the moment, Ernesto, is like, I mean, this is a formula for the inverse of this function suitably restricted. What is what is that restriction exactly? I mean, I know it doesn't, is it just I have to throw out z equals to 0? I mean, let's see here. Let me try to picture it. So z equals to 0 is like this, right? Y equals to 0 is this. right? I mean, sometimes you can understand like the extent of your mapping by studying the injectivity of it. So what happens if we set these equal, like, I mean, we have that. Z1 equals Z2, right? And we have like, then that, if Z1 is equal to Z2, then Y1 is equal to Y2, right? Because we get that. Huh. Is that right?
So it's injected.
Oh, that's weirding me out. Because it's definitely not everywhere injective by the calculation at the top of the board. Right? Oh. Okay. So this only happens if Z1 is not equal to 0. And this only happens if Y1 and Z1 are both not equal to 0. Because otherwise, yeah, you've got these, but that just gives you 0 equals 0. It doesn't give any information about x1. I don't know, I'm inclined to think that this is the inverse for f, where s is just like all of R3 modulo the xz and the xy coordinate planes. That makes sense because these formulas require division by the y or the z formula, the y or z coordinate. So yeah, the S has to be like the set u v w, right? Such that, you know, v and w are not equal to 0. Then that okay, anyway, yeah, enough. So does that make sense? Okay, cool. All right, so that's the inverse function theorem in a nutshell. It's pretty simple, really. You just, I'll go for it. Yeah. All right, let's see here. Now, again, we should probably come back and, you know, like try to prove it a little bit more completely, right? I have some other examples in the notes, right? But let's talk about the implicit function theorem now. And I believe you can use the implicit function theorem to prove the inverse function theorem. Or you could use the inverse function theorem to prove the implicit function theorem. So in some sense, they're like corollaries of one another, but I think it's good to see like separate proofs of them. But let's just start with a discussion of the whole problem of implicit functions. So a good example would be x squared plus y squared equals to 1, right? So here you're basically looking at f of x comma y equals to 1, right? It's a level curve. And the question then is, when can you solve for, you know, y as a function of x? Well, you kind of already know the answer, right? I mean, it's a circle, right? So if you want to be able to I'm trying to think of how to characterize it. So we can't. All right, let's see how to go. So I have to I can only approach these points like that. So like y square root of 1 minus x squared. So if I'm going to look for an inverse on not an inverse, if I'm trying to, so like here, basically I'm looking for f of, let's say, t comma g of t, all right, equals to 1 for, you know, t, an element of I, open, right? So like I'm looking for a way to solve the level curve equation, writing y as a function of x for all x in some open interval, right? I've used t instead of x just for the sake of, well, I can't I can't include the endpoints because if I go past it, then I'm up against the vertical line test. So like that's the best I can. That's all I can get away with, right? And of course, the flip side of it, right? I can do like this, right? I can go down here like that and up to there, and I have y equals, well, minus the square root, right? 1 minus x squared. And so the question is, what, if anything, does the calculus have to say about this pre-calculus of, like, you know, solving the equation for y, right? What is it about these points that's so special, is the question.
They have undefined.
They have undefined derivative. Let's see here. Let's think about this. F, right, is a mapping for us from R2 to R, right? So that means that the Jacobian of f actually has the form partial f partial x, partial f partial y. In fact, that is precisely 2x, 2y for this problem, right? And of course, that's the gradient vector up to a question of notation, rows versus columns, things like that. But yeah. So what is it? What is it about these points that's troublesome? Well, the thing that's troublesome about these points, right, is these are the places where partial f partial y is equal to 0. So let's think about this in terms of the linearization for a second. We can write you know, f of x comma y equals to 1 approximately at a given point as f of x naught y naught plus partial f partial x at x naught y naught times x minus x naught plus partial f partial y times x naught y naught times y minus y naught equal to 0. Well, equal to 1, right? I mean, I can approximate. And of course, then, this, by assumption, is a base point on the curve, so that's 1. All right, so like, what does this mean? This means that you have partial f partial x at the point times x minus x naught plus partial f partial y at the point you're interested in being near, at the point you're trying to solve for y close to, okay? Times y minus y naught equal to 0. And so what's the approximate solution here? Solve for y. That gives you the approximately the implicit solution to the level curve for y as a function of x. The first approximation, at least. The 0th one, of course, is the dumb one, which is just y of, y is y equals to y naught is the 0th approximation. So solve for y here, what do we get? Well, we get, I'm going to write it f sub x at p naught times x minus x naught, right? Divided by f sub y. See that division right there? Plus y naught. See, this requires that to be non-zero. That is why the implicit function theorem is going to say, as it applies to this context, if we have a function of two variables, we can solve for y if the level curve, if the defining level function is continuously differentiable, all right, at the point where, if it's continuously differentiable near the point where we have x naught, near the point x naught y naught on the curve, all right, and partial f partial y is not equal to 0. In that case, we can find y as a function of x close to the point. The proof of this, again, stems from an iterative procedure where you do this and then do this again, and then do this again, and then do this again, and do this again, and you can prove that that sequence of functions converges to a limit function, and that limiting function has the properties that you'd like, namely that it solves the level curve equation close to the point in question as advertised. Now, this is the implicit function theorem that you need to justify the differentiation we do in Calculus 1. I mean, think about this for a second. No Calculus 1 student will ever call you on this, but like here, at the start of Calculus 1, we do things like epsilon delta proofs, right? Which is pretty rigorous. And then all of a sudden we turn the corner, we do limit laws, we introduce the derivative, right? Maybe we prove some differentiation rules there. And then all of a sudden we're doing implicit differentiation. And we never really explain why, when you have an equation, right? If you have an equation that links x and y together, why is it that y has a derivative? We just assume it exists. We don't even really say boo about it. No one ever calls you on it, right? But like, just to circle back to Calc 1 for a second here, think about this. If you've got, y is equal to inverse tangent of x, right? So we trade that for tangent of y is equal to x. Well, see, the thing is, I know that y is I guess I know y is a function of x there because I started with it explicitly as a function of x. But it is somewhat comforting to think about the inverse function theorem here, right? Because if you differentiate that, you get what, like secant squared y, dy dx equals to 1. So we get dy dx equal to 1 over secant squared y, which is 1 over 1 plus tangent squared, which of course is the derivative of inverse tangent that we know and love. But depending on what you've proved or haven't proved here, we can use the inverse or the implicit function theorem to sort of support our claims that there is differentiability and that there is invertibility, at least locally. But anyway, I think I'm getting off track. Let's get back to the maps. Back to the maps. So, okay, so what is the question of the inverse implicit? Oh, before I forget, here. Another way to look at this is at the level of differentials. It's even more beautiful there. See, because if we've got x squared plus y squared is equal to 1. Well, if I take the differential of this, I get 2x dx plus 2y dy is equal to 0. And see, if I solve for this, I get dy is equal to minus x over y dx. Or I can solve for it and I get dx is equal to minus y over x dy. These coefficients actually are they will be like the ratio of minus fx over fy dx here, or minus fy over fx dy, for what it's worth. But the other interesting thing here is that if I want to solve for y, this formula shows me where I have to avoid. I have to avoid y equals to 0 if I want y to be a good dependent variable on x. And this right here says if I want to solve for x as a dependent variable of y, I need to avoid where x is equal to 0. We don't talk about this much, right? But the circle also we could look at as either this, right? Or that, where you're solving for like x is equal to plus or minus the square root of 1 minus y squared, right? We can look at graphs in x and graphs in y just the same. And the same theorem holds, like when partial f partial x is non-zero, you can solve for x. See, so there's really no the math is no respecter of x and y here. The implicit function theorem is symmetric with respect to x and y. It treats x and y on a level footing, the full statement of the implicit function theorem. But this is not the implicit mapping theorem, right? This is just the lowest, perhaps the lowest version of this. Let's talk about the real thing. So let me make sure I've got my my variables set up right, because like notation's everything here in terms of not pulling your hair out. So for convenience of exposition, we suppose that we've got like g1 of x1 through xm. All right, and then y1 through yn, and that's equal to, let's say, k1. And then I do g2 of x1 through xm, and then y1 through yn, and that's equal to k2. All right, and so we're going to look at a rather fantastic thing. We're going to look at a surface that is defined as the solution set of m plus n variables in n equations, n nonlinear equations. It's really quite fantastic what we're looking at here. Gn of x1, xm, y1, yn, right? That's equal to kn. So here we're looking at n equations in m plus n unknowns. Now you have studied this problem in the case that these are all linear equations, right? For sure we've studied that. But the question is, can we study it? Can we study it now? See, so let me recast this a bit. So what we're really looking at is like G vector, let's say, which is a mapping from Rm cross Rn to Rn, right? So you could almost look at it, I mean, you could look at it as like we've got g of x vector comma y vector, right? Equal to, well, k vector, I guess, if you want to write that. And what we're going to try to do here is we're going to hope that these n equations are independent in the sense that they at least allow me to solve for the y variables as functions of the x variables. So that kind of makes sense, right? Like, if you have m plus n equations in n plus n unknowns, you ought to be able to solve for, you kind of expect that your solution set has m degrees of freedom in it, you know? If the equations are genuinely independent, you'd expect m degrees of freedom, m as in mommy, degrees of freedom here. Now, so let me show you like the really slick way of doing it notationally. So if we have g of a particular point, right, g of x naught y naught equals to k, all right? Then if we look at the linearization of this equation near that point, what's it look like? Well, the linearization of this equation near the point in the vector notation would be something like this. Partial g, well, let me do the dumb thing. The dumb thing is, of course, the value of the level function at the point of approximation, right? Plus then partial g, partial x, and I've not even defined this yet, all right? Partial g, partial x vector at the point, all right? Times x vector minus x naught vector, plus partial g, partial y vector at the point, times y minus, now this begs the question, what do I even mean by these expressions at the moment, okay? But what I mean by them is not equal to 0, it's equal to what? It's equal to the k vector. So, I will elaborate on what I mean by those expressions here in just a second. But first of all, let's just get rid of some clutter, which is this, by assumption, is a point on this. I'm calling it a surface. I probably should call it a space. It's a, well, hopefully m-dimensional subspace. It's an m-dimensional manifold in Rm plus n, is what it would be. If you take m plus n dimensional space and you impose n independent equations, that should leave you an m-dimensional manifold in that space. That's the idea. And so the implicit function theorem is useful in that it helps us define submanifolds of Euclidean space as level sets of equations. So then what? I mean, so I guess the real question, of course, is what is all this? Well, remember that the Jacobian of G, right, would have been what? It should be technically, in terms of my variables, partial G, partial x1, right? Dot, 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 partial G, partial x m. And then you've got your partial G, partial y1, dot, 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 partial G, partial yn. That's just the usual Jacobian. If that's my nomenclature, that's my variables, set of variables. And so I think you can understand what the notation means now, right?